Yeah. Yeah. Well, it makes it like not boring, so like you actually have to try.
All right. Any questions? ODPs, PA2, PA3, Super Bowl, feeding. Meaning of life, you're in it, man.
CFE 2222.
No, life. Yeah.
Kind of about PA2 about freeing the memory.
Okay.
So you free it after you release the node, right? Or
After you delete a node, that's a good time to free the node that you deleted.
right after.
Yeah.
So
Otherwise, you lose access to it.
okay, so you don't want like a separate function for you just want a separate function, delete function. Free.
We made a separate one.
Okay, so there is no separate.
He means like the release node function from PA1. You don't want
Oh.
free to go in there. You can just put free in.
You can just free it, yeah. But then at the end of your whole program, you also need to go down your list and free each node. Right? Yeah.
So I just want to clarify, there's no release node function.
You don't need to write a release node function. You could if you wanted to. If you didn't want to change release node to free, if you were mimicking your old main program, you could make a release node that just calls free.
Okay.
But it's not required. And usually people would just call free.
Why'd we even write that function in the first place then?
In PA1,
Yeah.
because we didn't have a free.
You weren't able to free. It was in
Well, we could have just used that one instruction we put in there.
Yeah, but then you gotta find that instruction and replace it with free, and I wanted some symmetry. I wanted the idea that you call a function to release the memory.
Oh,
So that in PA2 it's the same kind of structure. It's not necessary. I just thought it might be helpful in some cases. So let me mention something that I've seen some people running into. So let's say this is our print routine, right? So print struct node list. So here's something I've seen people do. They declare a struct node named temp, and they say temp equals malloc. And then they say if list next equals null, return, and then they do something like temp equals list next, while temp is not null. And they print the current data and they move down the list and they go on and they return. And you run this and you get memory leaks simply by trying to print your list. Okay, what's the problem with this code besides the sloppy C syntax? Yeah, look at this and look at this. And what have we done? We lost the only thing that was pointing to what malloc returned. Up here we did malloc, that gave us a block of memory. We set temp equal to it. And then down here we set temp equal to a pointer to your sentinel node's following node. And there's no way to get back to this block. Now I could have, before I did this down here, said free temp to get rid of it. But then the question is, why did I do a malloc if I'm going to turn right around and do a free, and I never use the thing that I malloced? And the answer is habit, right? Because we're used to, if we don't malloc something here, a lot of times we get seg faults. If we try to use temp arrow data, we'll get a seg fault. So we get in this habit of using malloc to make sure temp points to somewhere, but it's not always necessary. It's only necessary to call malloc if you're trying to create a node in this case. For example, when you're adding something. But if your goal is simply to have something that will point to a node that already exists, you don't need to give it a value. And an example might be something like this. If I say integer I, and then I say print I, I'm going to get gibberish, because I doesn't have a value. So that's bad. Let me do this somewhere else. So if I say integer I, and then I say print I, that's going to give me some weird value. It's not what I wanted to do. If I say integer I equals 5, and then I say print I, that's going to work. It's going to print out the value of I. It's going to be 5. But here's what you probably wouldn't do. Integer I equals 0, I equals 5, print I. There's no requirement for doing this, because before I print I, I'm going to give it a value. Right? In this case, it doesn't do any harm setting I equal to 0. But if this is a malloc, it does some harm because I've actually allocated memory and I'm not using it. And I don't free it, it gets lost. So when you do this kind of thing, where you say temp equals malloc and then you say temp equals this, you're kind of doing this. You're declaring a variable, you're giving it a value, and then you're giving it a new value. Right? And it's not necessary. Sometimes we need to give it a value if we're actually going to use that variable. But if we're going to assign that variable to some other value, we don't need to give it an initial value. Okay, so that's in some cases where people are getting memory leaks even though they think they're freeing everything. Yeah.
Totally unrelated question.
Okay.
So, back when we were first looking at structs, I remember that you mentioned type def for the declaration of what the struct was. But I guess I don't understand why we put type def then and we don't use type def anymore.
You can use it.
What is type def?
So type def is a shortcut. So you can say type def struct node star, and a lot of people will call it like an uppercase node. And now every time that I would say struct node star temp, I can just say node temp.
Okay, so it just replaces struct node.
And node basically means struct node star. But it makes your code look cleaner to use type defs, right? Because we say integer I, we say character C, we say double F. But then for nodes, you say struct node star, and it's a different feel to it. So like this, we've just got a new type of variable called a node. If you want temp to be a node, you just say node temp. If you want it to be an int, you say int temp, and it makes it more consistent.
Okay. Is there any difference between using that and pound define?
I've never used pound define like that. So if you define something to be struct node star, I think that works.
So is type def a compiler thing?
Yeah, it's part of the C language.
Okay.
So when you're actually when you're initializing the struct node type, where would you put node in relation to like the brackets and all that? Would that be after the brackets but before the semicolons or before the brackets?
Yeah. You know like how you type that in the structure?
Oh, if you type def in the struct?
Yeah.
You put it after the
Like when you're first like writing out what a struct node is.
Yeah, so I think it would be type def, struct, node, curly bracket, full definition, close curly bracket, what you want to type def it to, and then a semicolon. I can't say I've ever actually done that. Yeah, okay. And you can put a star after the curly bracket to make it a pointer?
I don't need you to do that, but, because I usually just say like node star in my variable.
Okay.
Yeah. It'd be fine,
It would make that easier to read also, because if you have a node as opposed to a pointer to a node.
Right.
Make it easier to read. If you
Yeah.
just kept it at-
Yeah, so making this just a struct node might make more sense.
Yeah, that's what I was going for there.
Or you could have a node, and then you could have like a node pointer. You could have two types.
Also do that, yeah.
But after you write enough stars, this starts to look more obvious than this, right? So you get used to seeing the star. But it's all valid. There's probably a reason you shouldn't use pound define, but I can't think of an example where it would trip you up. But there's probably some difference.
Wouldn't pound define, like, I guess if you were to do it, you'd have to put like struct and star in like parentheses or something, or not parentheses.
Pound define will take everything after the thing that you're defining as part of the define. It'll like go off till the end of the line or a comment. There's a lot of stuff you can do with the preprocessor, because those pound defines can take arguments too. And so actually a lot of things in standard IO.H are actually macros that are defined, because it's cheaper than actually calling a function. So things that you can do in place. Cool. Other questions? Batteries died in my microphone, so I'm back to this microphone for today. All right, so queues. Via linked lists. So we saw how to do queues with arrays. The problem with arrays is that they have a fixed length, which means your queue has a fixed number of things it can hold. And unless you allow them to grow dynamically, that's kind of a hard limit. So if we use a linked list, we don't have an inherent limit on the size of the queue. We can keep growing until we basically run out of memory. So let's set up our Sentinel. I'm just going to call this queue. And I don't care what the data value is. And initially it's going to have a next node of null. Well, we like dealing with things close to the Sentinel, right? It's more efficient than dealing with things partway through the list. So with the stack, we always popped from the thing right after the Sentinel, and we pushed by creating a new node right after the Sentinel. And we want to do something similar with queues, but it gets a slight bit more tricky. So let's say we want to add the number 1 to the queue. Probably this is the right way our queue should look. Right, Sentinel points to a single node containing our single entry in the queue. That's a 1. The interesting question is, if we add 2, where should we insert that 2? Well, it's pretty straightforward to just insert it in the beginning, right? So we'll make a new node with a 2. We'll have that point to the last node, and then we'll change our Sentinel to point to this. And if we add 3, we'll do the same thing, and our queue will basically look like this. It'll look exactly like what we create with a stack when we push. So this is add start of list. So if we add to the start of the list, this is what our queue looks like as it builds up. Now suppose we want to remove. Which node should we remove from the list? We should remove this node. So we're removing at the end of the list.
You remove whatever is pointing to null, except the sentinel, in case it's pointing to null as well.
Say that again?
You remove whatever is pointing to null,
Mm-hmm.
except the sentinel node.
Right. Well, yeah. So how do we find this node? Well, one way to find it is to just start with the sentinel and move down until we get to a node that's pointing to null, right at the end of the list. Remember what the previous node was, change that thing's next pointer to be null, and then free the memory associated with this. So it's just like the delete function that we had for PA2. The problem with that is it's inefficient. Okay, add is always going to take the same amount of time no matter how big the list is. Have a million things in the list. If you're inserting right after the sentinel, make a node, point where the sentinel is pointing, have the sentinel point to your node, 3 steps, you're done. But removal is now an order n operation. Because if there's a million things in the list, you got to go through a million nodes in order to get to the last node that you want to remove. So order n is no good. We don't want that.
So if you just have a pointer ready that points at the head.
So let's have a pointer ready. And we can actually make it a piece of each node, even if we only use it in the sentinel. Let's have a head pointer that always points to the last node. It doesn't change when we add nodes, right? Because we're only adding in the beginning. The head doesn't move unless we do a remove. So now if we want to remove, we look at the head pointer. It takes us to this node. We know the value is 1. All we got to do is change the previous node to null and change the head pointer to point to that previous node. But how do we get to the previous node? If we had a doubly linked list, we could just follow back one. So one way out of this is a doubly linked list.
Couldn't you just point to the second from the back all the time?
We could have another thing, we could point to the second to the back, but then when we remove this, we have to change that pointer to point to the new second to the end.
You just always,
Still increases the operations. You end up using more power then instead of just having the double link.
Unless every node points back to a prior node, right? If we point 2 back to this node, then when we delete this, we've got to somehow figure out where this node is, because that's the second from the end. And unless this node has a back pointer, we're stuck again. So we can do a doubly linked list, but that's a fair amount of housekeeping, and I decided not to have you do a doubly linked list. So there's an alternative, and it may seem a little weird that this works in the same way that mirrors flip things left, right, but not top, bottom, that kind of experience. So here's the idea. Let's add at the end of the list, and let's remove from the start. And it sounds like kind of the same thing. And I'm going to use a third field here, which I'm going to call a tail pointer, which is always going to point to the last node. And we're not going to use this field for any of the other nodes. All right, so suppose this is what our list looks like. And suppose we want to remove a node from our list. Removal is now order 1, because we're just removing the node right next to the sentinel. So take what the sentinel points to, that's the data value we want to return. Change the sentinel to point where this node is pointing, So change that to point here and then free that memory block. So removal is now inexpensive, but what about adding? Well, if we want to add a new node, so let's say I did my nodes backwards. So assuming you added 1 and then 2 and then 3, right? 1 will be the first thing. So suppose we want to add 4. Well, the tail pointer tells us where the last node is. From there, we create a new node with our new data value. We change this tail node to point to our new node. We set the new node to point to null, and we change our tail pointer to point to the new node. And it's still order 1. And the reason it works is because we do have forward pointers, because it's a forward linked list. And in order to add something to the end of the list, we need to change the tail pointer from a current node to the node after it. And we already have a pointer for that. Whereas removing, we need to change the head pointer to the node before, and that's where we're getting into trouble. So if you do it like this, if you add at the end of the list and you remove from the beginning of the list, both operations take a fixed number of operations, regardless of the size of the list. Yes?
Wait, so the sentinel node is the only node that has the tail pointer?
Yeah, so you can use the same node structure, right, and have a tail pointer in these, but you don't need to use those locations, those fields. Alternatively, you could store the tail pointer somewhere else, but then you kind of lose the nice single data structure that you need to pass around. So this is a feasible solution. All right, so remove from the start of the list. That's just deleting the first element of the list. You've done that in ODPs, you've done that in programming assignments. And adding to the end of the list is just like inserting when you come out of your while loop in your add routine and you haven't added, but you use tail pointer to find what the address of that last node is. Make a new node, have the last node point to it, and then change tail pointer to point to the last node. So lots of pictures, lots of drawing and erasing and writing code to go along with the pictures, okay? Make sure you understand with blocks and arrows what it is you want your code to do, to add or remove, and then write code to do it. And it's actually pretty fun once you get it to work.
Would you care if we used a separate structure to hold the tail pointer and the sentinel, and then pass those to the functions instead of?
Yeah, that would increase your total size, right?
Yeah, each node would take a larger space, so if you had like a separate structure for the sentinel, and then all the other nodes are like how we've had them before.
So you can have a struct sentinel node, and then you can have a struct node,
Yeah.
right? And your sentinel node can point forward. It may get you into edge cases in your code, but if you want to go for it, go for it. I'm happy with it.
Okay.
But I don't want you to do just a straight doubly linked list. Okay, just because that's a little too straightforward. All right, well, what does an empty list look like? An empty queue. An empty queue, you've got your sentinel node, the next field is null. So you know there's no nodes in the list, no data nodes. And when you try to add something, remember we're adding at the tail, I would treat that as an edge case. Okay, if the list is empty, create a node, store your data, change the next to point to this, and go ahead and set your tail pointer to point to it also. And then you're off and running. When you remove from a list, remember you always remove the node right after the sentinel, so what do? You take the sentinel and you have it point wherever this first node is pointing. If that's the only node in the list, that changes the sentinel's next field to go back to null. And if you're not going to treat an empty list as an edge case, you got to make sure you put something reasonable in the tail pointer at that point, because there is no data node that's the tail of the queue anymore. So you got to either decide tail pointer is going to be null for an empty list or something. So I think the easiest way is probably just make sure the list is not empty. If it is, and you're adding something, set the tail pointer to the new node. But think about it. You can do it any way that you want that works. But there is an edge case when there's no nodes, because the tail pointer can't point to the tail, because there is no tail.
Also points to itself.
Could point to itself.
You could treat that as the list is empty.
Yeah. You can point it to null and use that as the list is empty. But you can also use if next is null, the list is empty. And I think if you do it right, if you point to yourself, maybe you can avoid an edge case. But you still need to set it to itself when you delete the last node. So play around with it, have fun with it. There's a lot of options. All right, so queue is empty if the sentinel's next field is null. That's definitely true. Queue is full, again, we don't know. If you try to malloc and you run out of memory, then the queue is full. But I'm not going to test that condition. Okay, so when you do your mallocs, check the return from malloc to see if it's null. You should always do that. And if it happens to come back null, the system is out of memory. At that point, you're fair just printing a message saying system out of memory, giving up, goodbye. Or saying system out of memory, add data not added to queue, and go back. But at that point, flames are probably coming out of your keyboard, so that shouldn't happen. All right, so a init again is just same as for a stack. You basically create an empty list, which means make a sentinel node, have it point to null, and return its address. So you might have a struct queue node star, and maybe you'll call it queue, and to initialize, call some kind of init routine. Same drill as PA2. Right, queue init does a malloc for a sentinel node, sets up the fields however they need to be set up, returns its address. So now queue is pointing to a struct queue node, which is a sentinel node. To add something to the queue, pass the queue itself and pass whatever you want to add to it, an integer. And if you want, you could return a success or failure value, so that if you run out of memory, you can actually register it from here. I didn't require that. To remove, you pass it a queue and you get back the value that you removed. But if you try to remove from an empty queue, what should you return? Well, it's fair to consider that an error condition for this assignment. So I'm not going to call remove on an empty queue, but you definitely want an is empty. That returns some sort of flag to tell you whether or not the queue is empty. And in your code, if the user says remove something from the queue, check to see if it's empty before you call remove. All right, the other option is you can do like scanf does. So remove queue, comma, address data, and return a status value. So when you call remove, you pass it a queue, pass it the address of something to hold the data. If it succeeds in removing something from the queue, it stores the value in this variable, and it returns, say, a 1. If the queue is actually empty, it doesn't change data, and it returns a 0. So that's the cleaner way to use error checking inside a remove function. But you can implement it however you like, as long as it works, as long as your main program doesn't throw up if you try to remove from an empty queue. All right, other questions on that? So let's look at this in full detail here, programming assignment 3. So we already went through the operation of the program, right? The details of how it should work. Switching between modes, adding and removing things, and so on. Make sure you free all your memory. Okay, so in a queue or a stack, you have a sentinel node pointing to a linked list. It's the same algorithm for freeing that you use in PA2. And when you remove a node, that's like deleting, make sure you free the memory after you removed it. And at the very end, just start at the sentinel, go through, traverse the linked list, and free things in your wake. All right, for the queue, so the head is the node right after the sentinel. Okay, that's what you're removing from. The tail is at the far end of the linked list. That's what you're adding to. Okay, so the head is immediately after the sentinel, tail's at the far end of the list. So you remove elements by accessing the node immediately after the sentinel. You add new elements by adding them to the end of the list. You must use some kind of tail pointer. Don't go from the beginning of the list all the way down the list to get to the end. Okay, I will deduct points for that, because that gets really inefficient as your list grows. So do this efficiently, some sort of tail pointer arrangement. And we've talked about a few options, including we've talked about a few options. Okay, so my suggestion here, augment the node structure, include a tail pointer. Just worry about it in the sentinel, use that to point to the end of the list. So again, don't travel down the list to the end, use a tail pointer field. All right, and the other stuff we talked about. So any questions on PA3? Sweet. So let's look at an application of queues to doing some path following. So let me make something that ultimately we're going to call a tree. Probably not going to go through all of these. So here's the idea. We have a starting point A, and we have a series of arrows from each location to possibly some other set of locations, except some of these locations don't have anything after them. They're dead ends. And if you're trying to find something, right, you'd like to be able to travel every path from your starting point to every ending point. Okay, this is called traversal. So you'd like to traverse this collection of data. This is a tree, it's also a graph. you'd like to traverse this graph starting from point A. So we want to come from A to B to E to K. We also want to go from A to B to E to J, and from A to B to D to I, and so on and so forth. And we talked about this with respect to stacks and running mazes. And so the maze running approach to this, which would be a depth first search, so depth first search, or a depth first traversal, would start at A, and it would say, okay, let's just take the leftmost branch as far as we can, and it would come down to K. And then it would come back up to E, and it would say, okay, let's see if we can go deeper from here. Let's go down this branch. And here it says, hey, I can go still deeper. I can get down to O. And that's a dead end. And it'll say, okay, was there a different choice we could have made at our last point? Yeah, we could have gone down in this direction. And that's a dead end. We come back to J. There's nowhere else we could have gone. Let's go back to E. There's nowhere else we could have gone. Let's go back to B. Hey, we could have gone down a different way. Instead of going here, we could have gone down to D and then down to I. And so it's visiting these terminal points that are very deep before it visits the ones that are less deep. For example, it's not going to come back to C until it's gone through all of this stuff. Okay, that's depth first. And we talked a little about how to do that with a stack. So let's look at a different way to do this traversal with a queue. And this is breadth first. And we're going to write an algorithm for this. So here's our algorithm. 1, start at, I'll just call it A. So how do we start at A? Add A to a queue. So we seed the whole algorithm by taking whatever point we're starting at and putting that into a queue. And now we loop. Remove something X from the queue. So remove whatever's at the head of the queue and put that into some temporary variable X. Okay. Add to the queue any point connected to X. And then go back up to 2. So what's going to happen if we do this? Let me put our queue down here at the bottom. So the first thing we're going to do is we're going to add A to the queue. That's step 1. It's a one-time step. Okay, now we're going to iterate. So we're going to remove what's at the head of the queue. That's an A. And so X is equal to A. And we're going to add to the queue everything that's connected to A, which in this case is just B. So we put B into the queue. Okay, so this is going to be our head over here, our tail over here. So we add from here. We add at the tail, and we remove from the head. So we've got a B sitting in the queue. Okay, and we go back to step 2, which says remove what's at the head of the queue. So we remove a B, and we set X equal to B. And step 3 says add to the queue any point connected to B. Well, what's connected to B? Well, we've got a C, and we've got a D, and we've got an E. So all of those get pushed into the queue. And we go back to step 2, remove the head of the queue. So we remove C, so X is equal to C. And we take anything connected to C and put it into the queue. So that's an F. And now we remove the head of the queue, which is D. and we set x equal to d. And we insert into the queue anything connected to d. So that's G, H, and I. So those get inserted into the queue. And we go back to the top. And we keep doing this. So remove the I, set x equal to E. So remove the E, set x equal to E. Add anything adjacent to E, so that's J and K. Remove the F, so x is equal to F. Insert anything connected to F. There's nothing connected to F, so there's nothing to insert. Remove the head of the Q is G. That becomes X. That's connected to L and M. Remove the H. That becomes X. H is adjacent to nothing, so there's nothing to insert. Remove the I. Nothing to insert because I isn't connected to anything else. Remove the J. That's connected to N and O. Remove the K. Not adjacent to anything. Remove the L. Not adjacent to anything. Remove the M. Not adjacent to anything. Remove the N. Not adjacent to anything. Remove the O. Not adjacent to anything. And when the Q is empty, then you're done. Okay, what did we just do though? Look at the values that Q had. It started off with the value A, and then it took on the value B, and then it took on the value C, D, and E. So first we visited this node, and then we visited this node, and then we visited these three nodes. And then we're going to visit F, G, H, I, J, K. And so what are we doing here? We're slowly moving deeper into this tree, this graph, right? But before we go down from level 3 to level 4, we're visiting all the things that are 3 hops deep from the beginning, right? Any node that is 3 nodes from the start gets visited before we visit all of these nodes that are 4 spots away. So this is breadth first. And it's a perfectly valid way of exploring a space. Okay, you can surf web pages doing a breadth first approach, which would mean you go through your first page, and every time you see a hyperlink, you click it and you read what's on that page. But you don't go any deeper than that. After you've read that page, you go back to your main page, you find the next hyperlink, click on that, read the page, go back to your main page, and do that until you've clicked all the links on your main page. Now you go back to that first deeper page you looked at and you do the same thing. Any links on there, now you click those. But you only read the page that it brings you to. You don't click on anything on that page. So you slowly go through all the pages that were 1 click away from where you started. It's a very unnatural way to browse the web, right? Because we like to follow tracks. We like to start here and say, okay, let's go here, and then let's go here, and let's go here, right? And then we're done, let's back up, and maybe we'll come back over here, right? This breadth first approach is very, very kind of quirky compared to how we normally sort of process information as humans. But it's a perfectly valid approach, and it has the advantage that if our graph, instead of being a tree, if it had multiple connections, so here's a starting point, I don't know. I'm not feeling very graphy today. Don't try to copy this. Right, so we want to get from this point to this point in the fewest number of hops. We can do this using a queue and doing a breadth first traversal of this graph. So what does that mean? We start here, and then we visit all the points that are 1 hop away from the beginning. Well, that's this point and this point. And now we visit all the points that are 2 hops from the beginning. So that's this point, and this point, and this point. Sorry, 2 hops from anything that we just circled. And now we find everything that's 1 hop from each of these things we just circled. That's here, and here, and here, and here. And now we find everything that's 1 hop from there, and that's going to be there. So this turned out to be a kind of goofy problem because they all have the same length. But if you do this, if you start at your starting point, you just go 1 step further and look at everything you can get to with that many hops from the start. As soon as you reach the destination, you know that you found a shortest path. Because the first time you reach the destination was maybe after looking at all the paths that take n hops to reach. And it's not possible that you could find a path with length 9, because you already visited all the points that you can get to with 9 hops from the start. So almost by definition, doing a breadth first search lets you find the shortest path through a graph from a start point to an end point. So that's one application. And if you've done 215, we've seen some of this, and we'll see some of this in 222 and 223. So queues are good for a number of things. So you get to program one up in your PA3. All right, any other questions? So we're done with ODPs for the week. Okay, I may post one Monday morning, but we're done for the rest of the week and the weekend. So no worries on there. All right, cool. I will see you next time then.